Hello, kiddos, and welcome to our last installment of acids and bases, the strength of acids and bases. Today we're going to take a look at strong acids, strong bases, how do you recognize them, and something called polyprotic acids, polyprotic bases. So enjoy. What do you remember, kiddos? Acids taste sour, turn blue litmus red. They have a pH less than 7. They neutralize bases. They react with active metals to produce hydrogen gas, which you know, that's really important. They react with carbonates to produce carbon dioxide. This, you're not going to be tested on, but just a little FYI. For bases, they taste bitter, they feel slippery, they turn red litmus blue, they have a pH greater than 7, and then neutralize acids. So a little bit of review for you on acids and bases. Strong and weak acids. The concept of strong and weak acids was developed to describe and explain the difference in properties of acids. Right? An acid can be described as a weak acid if its characteristic properties under the same conditions are less than those of a common strong acid. So for example, lemon is a weak acid. We can eat lemon because we can use it for our food. However, you wouldn't do the same thing with hydrochloric acid. It is considered a strong acid. And as you remember, or as you can, if you think about it, it's the amount of hydronium ions in the acid that's going to dictate if it's strong or weak. And today's lecture is talking about how do we know, how do we show that. There are relatively few strong acids, and you do have to memorize them. There are 6 to be exact, and I think there's about 3 of them in your data booklet, so you only have to memorize 3. So those are your 6 strong acids. 2, 3, 4, 5, 6. This one is an exception. We'll talk about that a little later. It's because of the subscript. It's a polyprotic acid. It's the only strong polyprotic acid. The difference, let's talk a little bit about the modified Arrhenius theory. Remember, with modified, it reacts with the water to form hydronium ions, right? Strong acids have high conductivity, high rate of reaction with metals and carbonates, and a relatively low pH. So the lower the pH, the stronger the acid, of course, right? These empirical properties suggest many ions are present. What that means is that there's lots of hydronium ions, which is consistent with the idea that strong acids react completely. What that means is more than 99% of it is going to react with water to form hydronium ions. And here's an example. Here's your strong acid, hydrochloric acid, right? It's going to react with the water. The hydrogen is going to react with the water to form hydronium ion. This will happen more than 99% of the time. This reaction occurs. This arrow also says that it's going to happen. It's a one-way arrow. It's not an equilibrium arrow. It's one-way arrow saying, listen, I'm just going to form hydronium ions, and more than 99% of the time is pretty high. And the only reason it's not 100% is we can't ever say that the HCl, this acid is 100% pure. Okay, so let's take a look at weak acids on the other hand. Empirically, they have low conductivity, a lower rate of reaction with active metals and carbonates, and a relatively high pH. Relatively high pH is like 3. It's not like 10, because that would be a base, right? So even a 3 compared to a 1 is low. Low in terms of acidity, higher number in terms of pH. These empirical properties suggest that there are fewer hydronium ions present, and why? It's because, based on the empirical data, the chemistry says that a weak acid reacts incompletely, kiddos. So it's actually going to react less than 50% of the time with water to form hydronium ions. So here's an example. Here's a very weak acid, right? So this hydrogen is going to react with the water. It's going to bring in that H+, right, to form hydronium. But this reaction here only happens less than 50% of the time. It could even be as low as like 1% of the time. This is something we're going to spend some time on in Chem 30. So this is something that may actually help you with Chem 30. Weak acids, because of this difference, weak acids are much safer to handle. And here are some examples. There's lactic acid in your body. That is something that's natural to us. Dairy has acids, teas, citrus fruits. Meat actually has some acid, and obviously carbonated drinks. Okay, here's some practice if you want to do it on page 255, 1 to 5. Let's talk about strong and weak bases. These are much easier to tell. If it has an OH, a hydroxide ion, in the chemical formula, it's a strong base. Pretty cool. They have a high electrical conductivity, fast reaction rate, and very high pH. So around 13, 14. Weak bases have a low electrical conductivity. When you're comparing conductivity, slower reaction rate, and a pH closer to, but greater than 7. How do we explain the difference? Same kind of thing, kiddos. With strong bases, all soluble ionic hydroxides. So an ionic hydroxide, remember, is a cation plus an anion, and the ion is the hydroxide ion. Dissociate completely more than 99% of the time to release hydroxide ions. So what you have is you have a dissociation. So here's my sodium hydroxide, an example. When it goes into water, just dissociates into the sodium ion and the hydroxide ion. This kind of stuff happens more than 99% of the time. However, a weak base is something like ammonia, where you do not have hydroxide in the chemical formula, but it does show empirically that it's a base. In this case here, we have a reaction, and we have our H plus reacting, right? It's going to leave forming the ion NH4 plus and the hydroxide ion. However, this reaction only happens less than 50% of the time. That's why it's considered a weak base, because it has fewer hydroxide ions, because it actually reacts less than a strong base. So explain the weak base properties of baking soda. Here's an example. Here's your baking soda. Remember, if there's a metal here, we dissociate, right? First, get rid of this. This is a spectator ion. Get rid of it. And then here is our base. So there's our base. Notice that there's no OH in it. There's no hydroxide, so we don't dissociate. But it does react with the water. We have our H plus moving out to form hydroxide. And then this is our, actually, believe it or not, this is actually called a conjugate acid. And you always get a conjugate acid when you're doing this. Now, you're not going to be tested on that. This is just a little FYI. Explain why sodium acetate has a pH of 8 when dissolved in water. Because if you take a look at this example here, here's my group 1 metal, so you're going to dissociate. Here's our base, kiddos. So there's our base. It's going to react with water. Obviously, you're going to get an OH, a hydroxide ion, but and here's your conjugate acid, and this is only going to happen less than 50% of the time. So it shows up as a weak base. And remember, with bases, you don't have to memorize anything. If hydroxide is in the chemical formula, it's a strong base. So there's some practice, page 257 if you want to do them, 6, 7, and 9. Let's compare, let's summarize. So strong acids have a very low pH, makes sense. High conductivity makes sense. Fast reaction rate makes sense. And completely react with water to form hydronium ions, more than 99%. And these percentages you have to know. Okay, so for weak acids, medium to low pH makes sense. Low conductivity obviously makes sense. Slow reaction rate. And partially react with water, less than 50%. This you have to know, kiddos. With a strong base, very high pH, right? Makes sense. High conductivity, fast reaction rate. More than 99% of the time it's going to dissociate, right? To your hydroxide ions. And another thing you can say here, anything that has the OH in its chemical formula is considered a strong base. For a weak base, medium to high pH, low conductivity, slow reaction rate, and partially react with water to form hydroxide ions, less than 50%. So it does not contain the OH, the hydroxide ion, in formula. Okay, so that's a pretty easy, I feel, understanding of a strong acid, strong base compared to a weak acid, weak base. So let's talk a little bit about polyprotic acids. Some acids only have one acidic hydrogen atom in their chemical formula. They're called monoprotic. These are examples of monoprotic acids. What that means is there's only one hydrogen. See that? There's only one hydrogen in each of these. Those are called monoprotic. They will only react once. Some acids contain more than one acidic hydrogen and can react more than once, okay, and that would be that here in the subscript, you're actually going to have more than one hydrogen. These are called polyprotic acids. There are some examples here. Notice here we have H2SO4. That little 2 is telling you that it's going to react actually 2 times. This H3PO4, it's going to react 3 times. You use the subscript to figure out how many reactions they're going to be. Okay, so use subscript to decide number of reactions. Okay, kiddos? So here's an example. Take a look at this 3. It's going to react 3 times. So let's take a look at what happens when there's a reaction, and then let's also take a look at the percentage you have to take a look at. Then you have to take a look at what's happening with the charge. Okay? Notice here, it's neutral. There's no charge. I am removing a hydrogen along with its proton, its positive charge. So you're not moving the proton, but you're moving the positive charge. That's where we get this, okay? Now notice, now we have H2PO4, I probably covered that up, plus a negative charge. There's a negative charge because I have an extra, a proton or a positive charge has left this particular compound. So now it has to react 2 more times. See that subscript? I covered it up. It has to react 2 more times because now it's H2. So let's take a look at another reaction. Another reaction, you have H2PO4. It's going to react again with the hydrogen to form hydronium ions, but now it lost another hydrogen. That's why there's an H here. Look at now at the charge, it's -2, right? Because now another positive charge has left. It has to react 1 more time. We have to do everything to get rid of all of those hydrogens. So here's the last reaction. It's going to react with the hydrogen. The H plus is going to move over there to form hydronium ion. Now you're left with no hydrogens and a charge of -3. This is the phosphate ion, and it's a polyatomic ion, right? And if it shows up in your data booklet, then you're good to go. Another thing before we move on that you have to pay particular attention to is that the first reaction happens less than 50% of the time. The second reaction happens less than 1% of the time. And the third reaction happens, that little sign, this little sign means about. So it happens, it occurs about 0% of the time. It's good times, eh? So that's it. That's a polyprotic acid, and that's how you break it down. So each of the resulting ions can react with an additional water to produce more hydronium ions, but these reactions are even less complete. As example, the third reaction here, about 0% of the time it's going to happen. So with all of these possible reactions, you might think that phosphoric acid is very acidic, but only the first reaction is significant. Also, the first reaction is only 50% complete, so it's actually a weak acid, and it has a pH noticeably higher than a strong acid. So here's an example. If you're just comparing the 2 kiddos, this is actually, obviously 1.7 is weaker than 1. That's all it is. It's just showing a comparison and of a weak and a strong acid. Based on this evidence, in general, polyprotic acids are weak, whose reaction with water decreases with each successive step. The only exception to this is H2SO4. Okay, it is the only strong acid that's a polyprotic acid, and the thing you have to know is that the first reaction is higher than 99%, and the second reaction is higher. It's about 50% complete. So it's actually we basically look at the first reaction, which is about 99% effective, and then out of the 1-ish percent, 50% of those are going to react again. So that's why H2SO4 is the only polyprotic acid that is considered a strong acid. So polyprotic bases, the same concept applies to bases. Some bases like CH3COO or acetate are monoprotic. And what we do for that is we take a look at the charge. The charge tells us how many reactions, okay? So actions. So a negative charge is going to tell you that only one reaction is going to occur. So it only reacts one time, right? So the hydrogen comes here, reacts, it brings with it a positive charge, right? This positive charge is going to make that neutral, forming the CH3COOH, which happens to be a polyprotic acid. And here's our hydroxide ion. This happens less than 50% of the time because it's weak, right? Because there's no OH in the formula. Others, like CO3 carbonate, CO3 2 minus, are polyprotic bases because they can react more than once with water, but their reactions are much less than 50%. So here's an example. Notice here that there's a -2 charge. It's going to react 2 times. There's going to be 2 reactions. The first reaction, the hydrogen goes there. Remember, it brings with it a plus, right? And here's my hydrogen. If I have one positive charge, it's going to take away it's going to neutralize one of the charges to leave us with a -1 charge. But I gotta react until that negative charge is gone. So it's going to react another time. So there's the second reaction here. The hydrogen is going to move over here. There's our 2 hydrogens, and it has a positive charge, which is going to neutralize the negative charge. That is why there's no charge here, and there's the 2 reactions showing that there's H2. It gained 2 hydrogens, not just 1. Okay, let me just go back and talk a little bit about that. Notice first reaction is less than 50%. The second reaction is less than 1%. And if there were a third, it'd be about 0%. Okay, it's always 50, under 50%, under 1%, and about 0%. Only with weak acids and weak bases, kiddos. So polyprotic bases continued. In general, polyprotic bases are weak bases whose reaction with water decreases with each successive step. Evidence shows that a carbonate ion solution is less basic than a strong base. And here's an example. We're comparing weak, right, to strong. And remember, with a strong base, you have the OH in the chemical formula. You're comparing 13 to 11.4. That's significant. That's about 11-ish times stronger of a base. So do not confuse a subscript here with a barium hydroxide, for example. Those are not polyprotic bases. This just tells you that when it dissociates, it's going to dissociate into 1 barium ion with a +2 charge, and it's going to dissociate in 2 hydroxide ions. This is just going to tell you it's going to form 2 hydroxide ions when it dissociates, okay? So here's an example of an acid, and I'll tell you to show me if it's an acid or a base. Now let's take a look at this. It's going to react how many times, kiddos? 2 times, right? So it's going to react with water. So I have to show that it's reacting with water. And what's going to happen is one of the hydrogens leaves, I should say. Sorry about that, right? And it's going to form H3O plus aqueous. Plus what happens here? We have 1 hydrogen left because only 1 reacted. SO3, and what's the charge on this, kiddos? Right, it's going to be -1. Does that make sense? Because I lost a positive charge and it was neutral. If I take away a positive charge, I'm left with a negative charge, right? Now I have a hydrogen here. I have to react again in order to get rid of that hydrogen. So I have H, and this is less than 50%. So I'm going to have HSO3 minus. It's going to react with water again. Oops. It's going to react with water. I was ahead of myself there. It's going to that hydrogen again. Is going to go and react and bring it with it a positive charge. So we have the presence of H3O plus. Now there's 2 hydrogens. That's because it reacted again twice, right? And oops, wrong way. I'm going in the wrong direction. No more hydrogens. So I have SO3 2 negative. Take a look at your polyatomic ion chart, and that should be a thing. And if it's there, you're on the right track. So now there's no more hydrogen, so my reactions are over. Okay, makes sense? I needed to react that last hydrogen, and here we have it. It's being used up when it reacts with the water to bring over the H plus to form my hydronium ion. And I'll give you one example with a polyprotic base. So notice that this is a metal. So let's go ahead and dissociate first. We have 3 beryllium ions, right, with a positive 2 charge. And then we also have 2 phosphate ions with a -3 charge. Okay, this is just gonna not worry. You're not gonna really worry about that. It's just most what are they called? Most metals are gonna just dissociate and be spectator ions. So now I'm gonna go ahead and don't worry about this. This just tells you what happens twice times 2. So you don't have to show that in your example or when you're writing it out. So I have PO4 3 minus. Guess how many times it's going to react, kiddos? Look at the charge. It's a 3 minus charge. It's going to react 3 times. So let's go ahead and react with water. So we have our water here. And what's going to happen is a hydrogen is going to move in this direction when it reacts, bringing with it a positive charge, which then, let me just put this in because we know that it's a base, so we have OH for sure as one of my products. Now we have HPO4, 2 negative. It's 2 negative because it started off as 3 negative, right? But we added to it a positive charge, so that just got rid of a negative charge, so we have 2 negative. So now we have to react 2 more times, right? So HPO4, 2 negative, plus H2O. This hydrogen is going to react again, and it's going to bring with it a positive charge. It's going to yield a hydroxide ion. And my next product is going to have an extra hydrogen. Now it's not 2 negative, it's 1 negative. So it's going to have to react 1 more time because there's still a charge here. So I have H2P, oh my gosh. Let me just rewrite that so it looks pretty. H2PO4 -1 plus H2O liquid, right, is going to yield, it's going to react. So now we have my hydroxide ion, because it's a base, correct, plus H3PO4. This time, there's no charge because we start off with a -1, and we added a positive to it, so now it's completely neutral. This is the thing. This is actually an acid, okay, your conjugate acid. So in this case here, less than 50%. Do you recall how it goes? Less than 1%, and about 0%. All right, that's it, kiddos. There's a little bit of practice for you, but really not a bad day. Have a great day, kiddos. We'll talk to you later. Bye-bye.